Hi everybody, my name is Adam Wolk. I'm a technical program manager at Microsoft for PostgreSQL. Today I'm going to talk about fuzzing PostgreSQL and knocking at its door essentially. You will learn what fuzzing is, how to start your journey with fuzzing, and if it is for you and how to approach a large complex code base like a database. Okay, let's start throwing some stuff at the database. So first off, what will you get out of this talk? You will learn if fuzzing is for you, how to start, and how to approach a very complex software like PostgreSQL, for example. So who am I? I'm a principal program manager for PostgreSQL at Microsoft. I'm also an OpenBSD committer, but slacking for the last few years. I have background in information security and systems programming, and I believe that operating systems, databases, and web browsers are like a flavor of the same thing. And yes, I actually worked on all of those on operating systems via OpenBSD and FreeBSD at my previous job, databases via PostgreSQL, MySQL, and Oracle. And for browsers, I'm actually a contributor to the Otter browser, and I happen to port Dartium, which is a Chromium fork, onto the BSDs. I'm a contributor to many, just inconsistently productive. So the agenda for today is what is fuzzing. We will go through a toy example also, why you should fuzz a database like PostgreSQL. We will figure out what are some good fuzzing targets, how to fuzz networking, which is a gnarly beast, and we will go through some conclusions. Okay, so first off, you may have heard of testing, which is figuring out how to check stuff. But there's a different form of testing. You can call it adversarial testing, for example. When you have a system and you want to look for some security problems with it, uh, you don't have necessarily the access to the source code. And you can imagine this was there since 1988, for example, where first mentions of random input testing have been around since. And you can imagine, for example, a web server and somebody throwing HTTP requests at that web server and seeing what happens with the web server. And they can throw random garbage at that web server and see it fall over, or just continue buzzing. And with that testing, they may find bugs, may find security bugs, or nothing interesting may happen. This is not consistent, right? Like you don't know what happens inside the black box, and it takes a long, long time to find any issues with that. So then people started doing smarter things, right? It's still a black box, but you know a bit about the black box. If this is a web server, you know it takes HTTP requests. So maybe don't throw completely random garbage at it. Maybe start mutating the inputs so that they are still valid HTTP requests, but slightly malformed, right? So you're covering a more likely path that a program can take. Or if this is a database, maybe you're not throwing random strings at it, but you're throwing mangled SQL statements, which are more likely to trigger inner paths of the code base. And you can employ some more advanced algorithms on your inputs, like genetic algorithms, to get more interesting inputs. Later on, you have instrumental fuzzing, and this introduces a feedback loop. So you can imagine this puts probes inside of the web server in a way that you would understand what's happening as your inputs are executing onto it, right? So if you were throwing things as an elephant, right, like you could throw random stuff out at it, you don't know what's happening inside of it. But then maybe you can approach it and maybe, put a stethoscope on it or have an x-ray, then maybe like throwing that banana did something to it that you didn't see from the outside. So what is fuzzing? Fuzzing is automated testing that throws unexpected inputs. It often will trigger crashes, hangs, memory bugs. It uses coverage feedback to find new ways to get deeper into the program. It finds weird, non-obvious bugs that go very deep into the code base. It's especially useful for certain areas like parsers, security critical code, and protocols. Let's go maybe to a sample toy program to like get the concept uh, hammered in. On the left-hand side, you see a C program. It's not very important what it does in general, but it has a deliberate crash in it. You can look on the flowchart on the right, which represents like all the instructions that are in the code. There are 6 branches denoted by uh, the forgot the word. Okay, there are 6 branches that have to pass in order to reach the crash. What a fuzzer like AFL would do is a small piece of code. It would add a small piece of code into each branch to know which code paths were taken and which were skipped. So if you would trace the execution of this program, starting with a random input, you can see the input string here in the upper left-hand side. It's an empty string. We can see that the first highlighted line is a length check. It checks if it's 0, then the program will exit. So since it's 0, the program exits without a crash. We have not reached our error condition. So we may speed up things a bit by giving the fuzzer a better input seed. So instead of an empty string, we will start with the text test. And this allows us to jump past the first check of length, and we would fail on the second check because the first character is a T, not an F. But the fuzzer knows that the previous input opened a new code path. We got a bit further into the binary. So it will use this as a basis for further mutations on the input data. Applying various strategies on the data, it will expand, change various letters, do many manipulations to the string, resulting in newer strings. And this way, the fuzzer actually starts to see new code paths. We are getting further into the program as we are keeping mutating the inputs, right? So we see the first 2 letters were kept from the previous iterations, and we have a new mutation that will fail, but on the next mutation, we pass, and on the next, we finally passed the whole first if statement, and we are into the second if statement, which actually looks for the string crash in the input. We don't have a string crash in our current input, which is fuzz OC, so the program will exit again with return 0. You can see it here on the flowchart. After some more executions, this is an actual input stream that a real fuzzer found. And you probably wouldn't come up with this specific one. It's not like the most intuitive one a human would come up with, but it actually finds a valid string that makes us go through the whole execution tree into the final crash. Now, I mentioned that I'm using a fuzzer, so let's talk a bit about fuzzers. What you see on the screen is a screenshot of the American fuzzy loop, AFL for short. This is how our sample program would look like, run under this fuzzer. And American fuzzy loop is a security-oriented fuzzer that employs a novel type of compile time instrumentation and genetic algorithms to automatically discover clean, interesting test cases that trigger new internal states in the targeted binary. It was created and popularized by a Polish security researcher, Michał Zalewski, also known as El Kamtów, who at the time worked at Google. On this screen, and I know it's a lot, but the details are not that important. It's a screenshot of another tool running our program. This tool is called Honggfuzz, and it's a general purpose fuzzer that uses code coverage, software and hardware based, to find bugs and it is multi-process, multi-threaded, and supports persistent fuzzing for extreme speed. This is a report that a fuzzer would generate. This one is actually from our toy example, and it shows some details in the file that it spits out that contains the input that it used to trigger the crash that it found. And here you can see me invoking the toy program and I'm passing to it on standard input this file that the fuzzer produced. And you can see the program printed boom and immediately crashed. Segmentation fault, core dumped. In the next line, we print out the content of the fuzzing file that we fed into the program, and you can see it's the weird string that we saw in the previous slide, which is fuzz crcra crash. Now, the interesting thing with fuzzers is they learn by observing the software, and by that they can figure out very complex patterns like XML format, HTML format, programming languages. There's a great blog post by the author of our AFL called Pulling JPEGs Out of Thin Air, and it's exactly about that. They start with like an empty file and fed into AFL running some image parsing software. And after about 6 hours on an 8-core system, it got its first very unassuming image, a blank scale, 3 pixel wide, 784 pixel tall image. But the moment it is discovered, the fuzzer starts using the first image that it found as a seed, rapidly producing a wide array of more interesting pictures for the new execution paths. And what you see here on the screen is taken from that blog post, and it presents a sample set of images that AFL found, knowing nothing about how to create not only images, but also the image format that's needed to store and represent an image on disk of a computer. So why would you want to fuzz software? Testing is polite. You assume or you know the interface of a program, you approach it, you test it in a polite way. You knock, you pass things that are expected, and you get results. Fuzzing is rude. It doesn't go to the door, it goes through the window or through the back door. When that happens, assumptions break. And when assumptions break, you see bugs appear. So an unexpected piece of input in one part of the code base can result in something 3 parts later failing in an unexpected way that will cause your program to crash, collapse, or enable an attacker to gain escalated privileges. Many existing databases use fuzzing extensively. SQLite has a reputation for bulletproof reliability, and it is strongly tied to their fuzzing investment. They use continuous fuzzing using OSS fuzz and DB-SQL fuzz, and has fixed real issues because of that. One of the first bugs found with AFL was a pre-authentication MySQL remote denial of service via integer overflow, and it was affecting MySQL in a way that an unauthenticated attacker from the network could cause the loss of availability of a target database by simply sending some packets over the network to the database. So why fuzz PostgreSQL? Databases are like operating systems. It's not one attack surface, it's many overlapping ones. Traditional testing assumes that you know the inputs, you have expected control flow, you have stable invariants. And PostgreSQL breaks all three. Inputs come from untrusted clients. Execution paths depend on planner decisions and invariant change across versions, roles, and configurations. And with such a huge surface, how do you select interesting fuzzing targets? So here is a graphical representation of some, not all, subsystems in PostgreSQL. And you can think of that like as an attack surface complexity map. And if you look at some parts of it, like the most obvious one would be the SQL parsing. There are plenty of existing tooling that can smartly mangle SQL, and it's easy to test and fuzz, as you can simply connect and execute queries against a server. It's a high reward area to test because SQL injections are still a common class of software errors, and hence vulnerabilities within it can lead to wider exposure. There are some existing nice tools like SQLsmith that generate valid schema-aware SQL statements. Uh, in this section, you can also find other parts that are worth exploring, like the SQL lexer parser, the copy input format for like JSON, XML, and CSV. PostgreSQL is a very extensible database in so many ways that it only increases the potential scope of things that can go wrong. So some existing extensions that are interesting surfaces are page inspect, L3, HStore, pgcrypto, and custom C extensions. Also foreign data wrappers, because that introduces network file input from external systems into your system. But there are also extensions that hook in very deeply into PostgreSQL, like TimescaleDB or Citus. And those can have implications of the behavior of the whole system. There's a whole replication subsystem, how logical decoding works, replication slot behavior, hot standbys, anything related to handling files, so storage and WAL, file and data formats. So, for example, storage and page logic, heap page readers, tuple decoding, index access methods, utility and DDL function paths like alter statements, create statement, reindex commands, and table partitioning logic. Now, there's also the networking protocol. It's a high value target because it's external, right? Like with the MySQL example, you may not even need to be authenticated to send data to the database and have unexpected results. Especially because of that, the libpq startup packet feels like a good vector of attack and also a nice target for fuzzing itself. So I'm not the first one who had this idea. There are some talks from online recorded from 2023-2024 by Nikolai Shaplov from Postgres Pro, where they describe their approach of fuzzing PostgreSQL. They found at least 3 bugs in the database, and they selected the same targets as I, but with a different approach, which will be nice to compare a bit later. In 2020, also, there was this paper testing database management systems with language validity and coverage feedback. And Squirrel ran for 11 days on PostgreSQL and MySQL, found 63 bugs, 51 from SQLite, 7 from MySQL, 5 from MariaDB. They haven't found bugs in PostgreSQL, but they focused on the query parser, which I think is a very hardened piece in the database today because it's also very easy to test. The Google runs like an OSS fuzzing project, which consistently runs fuzzers across many databases. It's so far, like at the time I checked, found 19 SQLite bugs, 15 from MySQL also, 0 from PostgreSQL over a span of 3 years. So what are the challenges in fuzzing PostgreSQL, especially areas like networking? So first, PostgreSQL is not one target. It's a stateful, multi-headed system where every input wakes something up. There's a socket per connection because there's a process per connection also. There's TCP/IP overhead that requires setup and delays. You have complex persistent state between connections that can impact other connections, right? Because every SQL statement may result in some files being modified and stored persistently on disk, and that can impact further executions. PostgreSQL also is heavily defensive. It handles a lot of errors. It interjects signal handlers in C code. It has long jumps in the code for error handling, and it traps a lot of exits. So it's very hard to distinguish between, oh, the database crashed versus the database figured out something is wrong and decided to shut down, which is a completely different state. So how did PostgreSQL Pro approach it? They evaluated running PostgreSQL in single mode and decided against it because they wouldn't have parts of the system they wanted to test available, like the networking stack. What they decided to do is modifying the database in a way that connecting to it will not spawn a new backend process. Instead, it would remain as a single process system. They started using BetterFS file system for snapshotting, and they replaced the networking codes with their own implementation, hijacking the networking code, and that way they fed inputs from the fuzzers into a running database. That's a very nice but very complex setup. I approached something simpler, which is I isolated the code I wanted to test. Then I wrote simple test harness programs, small programs that called directly the parts of the database I wanted to test and fed it the input data from the fuzzer, hoping that I would hit some errors. So here's an example of the fuzzer running on PostgreSQL using my method. It's very slow. You can see only 40 executions, almost 40 executions per second. It even says it's slow. And it's slow because I run it with full code coverage because I wanted to show you what parts of the code are hit or not. If we go on the next screen, I know this is a very big picture, but it's just overview. This box here is another fuzzer running, slightly faster because 7,000 times a second. And in the background, you can see code colored with lines hit and not hit. If we zoom in a bit, you can see that in the line of the if statement, if we zoom in on it, you can see we took 3 paths and 1 we didn't. So a plus denotes a path we took, a minus a one we didn't. And if we focus on the next if statement, we never hit a length more than 0. This is because when I was calling this function, I provided a hard-coded length. And since the fuzzer didn't control the length variable, it never attempted something different. So I could have been running this for months and not find a single bug because it would simply never go further. The fix for that, of course, is making the other parameters also parts of the fuzzer input, and that allows you to explore deeper into the PostgreSQL codebase. So also be mindful to check things. So I personally have not hit very big bugs, mostly because PostgreSQL is a defensive code base, so it handles a lot of errors, like I mentioned, and it's very well battle tested. I had very slow test cycles, so I was running on a local laptop with code coverage enabled, and not for a very long time. So what could be done next is testing on bigger hardware and maybe adding entry points for fuzzers to PostgreSQL. So every fuzzer has like a special batch mode. So if you design specific entry points for them, they are able to directly invoke code from the database without setting things up themselves. So that makes testing easier. So if I were to continue on to this, I would say run more fuzzing. There's plenty of room for everybody to try, and run it for long and repeatedly, especially after new releases and new changes. So with that, I hope that you come out from this excited to try fuzzing yourself and dipping your toes in testing new places. There are also very small programs in PostgreSQL like pgdump, for example, that could be good fuzzing targets that wouldn't require setting up the whole database for testing. Thank you.